Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the specific heat, internal energy, and enthalpy of ideal gas. We defined an ideal gas as a gas whose temperature, pressure, and specific volume are related by the ideal gas equation of state. It has been demonstrated mathematically and experimentally that for an ideal gas, the internal energy is a function of the temperature only, that is, U equals UT. In his classical experiment, George submerged two tanks connected with a pipe and a valve in a water bath as shown in the figure. Initially, one tank contained air at a high pressure and the other tank was evacuated. When thermal equilibrium was attained, he opened the valve to let air pass from one tank to the other until the pressures equalized. George observed no change in the temperature of the water bath and assumed that no heat was transferred to or from the air. Since there was also no work done, he concluded that the internal energy of the air did not change even though the volume and the pressure changed. Therefore, he reasoned the internal energy is a function of temperature only and not a function of pressure or specific volume. George later showed that for gases that deviate significantly from ideal gas behavior, the internal energy is not a function of temperature alone. This expression can also be obtained from the first law. For a closed system, the first law is: since no heat was transferred and no work was done in this case, we then have zero change of the internal energy in this process. Since U is a property, we can suppose it depends on the temperature and the pressure. The total differential can then be expressed as: since there are du equals 0 and dp does not equal 0, we can then conclude that U has nothing to do with the pressure, and then it depends only on the temperature. Again, we can also suppose the internal energy depends on the temperature and the specific volume. The total differential can then be expressed as: since there are du equals 0 and dV does not equal 0, we can then conclude that U has nothing to do with the specific volume, and then it depends only on the temperature. Therefore, the internal energy depends only on the temperature. Let's give examinations of U only depending on T. Thermal energy includes internal kinetic energy and internal potential energy. The internal kinetic energy depends on the temperature. The internal potential energy depends on the temperature and the volume. The study of gases from the microscopic point of view shows that the dependence of the internal energy of a gas on pressure or specific volume at a specified temperature arises primarily because of molecular interactions. Accordingly, as the density of a gas decreases at fixed temperature, there comes a point where the effects of intermolecular forces are minimum. The internal energy is then determined principally by the temperature. Ideal gas has no intermolecular forces. U is only determined by internal kinetic energy, so it is only a function of T. For ideal gas, does H also depend only on T? The answer is yes. By the definition, we can conclude that H also depends only on T for an ideal gas. For general working fluid, the specific heats Cv and Cp are expressed as the specific heats for ideal gas Cv0 and Cp0 are expressed as UHCv0 and Cp0 of an ideal gas vary with temperature only. A specific relationship between Cp and Cv for ideal gases can be obtained by differentiating the relation H equals U plus RGT, which yields the relation. For ideal gas, we have this is the Mayer relation for ideal gas, or Mayer's formula. The Mayer's formula reflects the relationship between the constant pressure specific heat, the constant volume specific heat, and the gas constant. The Mayer's formula shows that although the constant pressure specific heat and constant volume specific heat of an ideal gas are both related to temperature, the difference between the two is independent of temperature. At this point, we introduce another ideal gas property called the specific heat ratio. The specific heat ratio is defined as: for ideal gas, we have the specific heat ratio for the ideal gas kappa or gamma 0 is also known as the ideal gas adiabatic index. Okay, that's all for this task. Thank you very much and see you next time.